Hey class, so today's lecture is going to be a little shorter than the rest. Last class before spring break, I I don't want to teach you too much and on the chance that you end up not studying a whole lot over spring break and forget most of it. So we'll take it a bit easier today. I'm quite certain that I'll reclaim the time with the optional videos on one-off things that you can do in a Linux environment, in a shell, in a terminal, inside a terminal, as well as other various introductions to coding projects or whatever other one-offs I find that I think might be interesting to you or helpful down the line for you. Okay, so let's run through the chapter on trees, and then we'll be done until after spring break. Okay. So trees are, you can read this introduction yourself, right? But trees are used to represent hierarchical structures, such as organizational charts that a business might use to represent a chain of command, or an HTML document object, right? The document object model has as a root of a tree structure the document, and then everything else flows from that, and we'll take a look at that whenever we come back from spring break. Such a structure would also aptly represent the executive branch of our government, where every employee reports to exactly one manager until you reach the top, i.e. the chief executive. Okay, so as we discuss these and as we introduce the definitions, I want you to think about these examples that will kind of help you fix in place what the concept of a tree is. Even though, in terms of family tree, it's already something that should be familiar to you on some level. Okay, so a tree is a particular type of graph, so named because such graphs resemble inverted trees. It is a connected, undirected graph with no simple circuits, right? And so the no simple circuits is really the requirement here. Okay, so we have our first theorem. An undirected graph is a tree if and only if there is a unique simple path between any two of its vertices. So if there's only one way you can get from A to B, and that holds true for every pair of A and B in your graph, and it's connected, right? And then you've got a tree. Your graph actually represents a tree. And as with other data structures, the more structure you have, the more particular your object is, the more additional properties you can state against it. So it's always nice to know that if you have something that is more specific, right? So more general handles more cases. If you improve something against a general case, then it's to your advantage because you're able to prove it to a large class. But in terms of usage and in terms of guarantees provided to you by that structure or by that, whatever object it is that you're discussing, greater specificity is always to your advantage to know what you're dealing with. Okay, so back to definitions. A rooted tree is a tree in which one vertex has been designated as the root and every edge is directed away from the root. Okay, so here we have this theorem that tells us how just some general undirected graph might satisfy this property, right? That there's a unique simple path between any two of its vertices. Unique being the key word there. And so, but it doesn't imply that we have some beginning, some root. And so we modify our interpretation of how we can see the presence of a tree inside of a graph, inside of an undirected graph, and say, okay, well, we can call it a rooted tree if we pick one node to represent the root. Okay. So another definition: a rooted tree is called an M-ary tree. Think binary tree or ternary tree or four-ary tree and so forth. if every internal vertex has no more than m, right, than m children. The tree is called a full m-ary tree if every internal vertex has exactly m children. An m-ary tree with m equals 2 is called a binary tree. Right? And so binary trees are something that we'll discuss. It's convenient because it's the minimum breadth tree that isn't just a straight line, right? That isn't a linked list. There are choices as you go from root down to leaf node. You're permitted choices. You can go left or right. You can make these decisions, and so you can take advantage of that whenever you're storing data or whenever you're evaluating the behavior of an algorithm, and we'll discuss that later too. So binary trees, where you have left and right children, are a particular interest to us as computer science majors. Okay, so next definition: an ordered rooted tree is a rooted tree where the children of each internal vertex are ordered. Typically, they are drawn in ascending order from left to right. So in this case, you could call them children 0 and 1, or left and right, or first and last. Note that an HTML document is an example of an ordered rooted tree. And again, we'll explore this, but if you get a like a div object in HTML, so if you get the reference to it, then you'll see that it has a children property, and that children is an array, and it's the or an array-like structure, and it holds all of the immediate children of that particular node, that div tag. So it might be text, it might be text nodes, it might be buttons, it might be a form, it's whatever is inside of that div, and the children are ordered in this fashion. So these to some extent, these terms like ordered rooted trees and rooted trees, or whatever, are a little bit formal. Typically, whenever we think of a tree, we think of it as having a lot of these properties already, such that if you have a tree, well, typically we represent it with a reference to that root node, so it would necessarily be a rooted tree, and the children have to be stored in some collection, and the collections are generally iterable, so it would be an ordered rooted tree. So it's it's somewhat academic that we have this distinction of term here, but whenever we discuss these as abstract objects, as something where a tree spontaneously appears, as an alternate representation of a graph, which is very much not rooted, then these additional modifiers are helpful. But in the programming context, once you're dealing with it, you're typically going to have an ordered rooted tree, and so you'll find yourself referring to it just as a tree, because it's what you necessarily have whenever you're programming it, unless you go out of your way to not have that. Okay, so a little bit of extra terminology. Right? So the nodes of a tree will have one of three classifications. There's the root, there's some internal or interior node, and there's the leaf nodes. The root is the entry point to the tree, so it's the reference that you hold in order to get to traverse the tree or perform any actions against it, either read or modification. Okay. The interior nodes, a tree node which has at least one child. The root is a special case of this and is always considered interior. But any other node that has at least one child is considered to be interior or internal. And the leaf nodes, which are the nodes with no children. So just like a tree with leaves, right? The leaves aren't branches, right? The interior nodes would be the branches. The leaves are kind of where the tree stops. They're the surface of the tree, essentially. So a node with no children, in traversal algorithms, these nodes will and must satisfy halting criteria for recursive methods. So you don't iterate past the leaf node whenever you're recursively traversing a tree, because it's pointless. They don't have any children. So if your algorithm is attempting to, then it's going to throw an exception, or it will throw a different type of exception. Right? So that'll either be a Stack Overflow exception or a null reference exception if you try to get into the children of a leaf node. So as you're writing it, it's always nice to know when your recursive function calls will stop attempting to go deeper and will start returning back up the stack. Okay, but we'll discuss all that once we start coding more. So it is possible for the root node to also be a leaf node. So this is the case whenever the tree consists solely of the root node, in which case it would be considered both interior. It would be all three. It would be the root node, interior, and leaf node. Okay, so in a binary tree, back to definitions. In a binary tree, if an internal vertex has two children, the first child is called the left child, and the second child is called the right child. The subtree rooted as the left child is called the left subtree, and that rooted at the right child is called the right subtree. So just like we had subgraphs, we can have subtrees, and in this case, because there's this hierarchy going from parents down to their children and so forth, and to further descendants, you can just consider the subtrees of really rooted at any interior node. So if you want to think of it like your family tree going back to your 8th great-grandparent, right, then you can consider the subtree as just the family tree that began with your grandmother on that line or whatever. Right? So you would have this subtree, and it would be one of the descendants of the full tree, the proper full tree. And so, as we're referring to them, whenever we start breaking them up and discussing these smaller components of the tree, the subtrees, we'll typically just say the left one or the right one, meaning the one that's rooted at that left child or the right child. So you'll pick up on that pretty quickly. Okay, so examples of trees, right? These things with which don't have simple circuits, right, would be saturated hydrocarbons, where you have this chain of carbons, and then each one of them is singly bonded to the nearest carbon neighbor, and then all of the other valence electrons are paired up with that of a hydrogen atom, right? So that you have this fully saturated hydrocarbon. Or any molecular structure with only single sigma bonds, which may be represented using a tree structure. And they tend to have labeling that indicates some beginning and then the branch points and so forth. So if you study organic chemistry, you'll see that there's this convention for where you begin naming the molecule, and then all of these rules for extending the name to describe when you have a branch point and so forth. Whenever you have a carbon that's bonded to two other chains of either carbon chains or whatever, or lipid chains or phosphorus chains or whatever. Okay. So the organization chart for a company with a chief executive officer or chairman of the board of directors may be represented as a tree structure. And then another example, a computer's file system may also be represented as a tree structure. We've discussed that before. Okay, so now we have a theorem. A tree with n vertices has n minus 1 edges, and you can prove this inductively. So you start with one vertex, just the root node, and then there are no edges. You give it one child, and it's connected to the tree in its previous state. by one edge. So one new vertex implies one edge to grow the tree by one, right, by one node. And so if you add another one, then you'll add one vertex and one edge to join it to the tree, regardless of which node you join it to. And so that this is inductively maintained, that in order to get to n vertices, we had to add n edges. And we began with one vertex and 0 edges. Right? So that we always have one more vertex than edges. Okay. So next theorem, a full M-array tree with I internal vertices contains n equals mi plus 1 vertices. Right? So we're given that it's a full tree, so that if m is equal to 4, right, then every internal node, every internal vertex has exactly 4 children, and the leaf nodes have 0. So then we have this formula that the total number of vertices is, well, each internal vertex, since it's full, has exactly m children, right? So m times I, in the example we gave, 4 times I, and then plus 1 vertices. Right? So we're counting all of the children, right, and all of the internal ones, and then we add 1 for the root. Right? Okay. So I guess in this example we are not counting root as an internal vertex. So we got to be careful about how we define that and what convention. But I wouldn't worry too much about it. So you just want to make sure that you're accounting for all of the children that can be done. And whenever you try and come up with the rules for these, or to count the vertices, the number of vertices and the number of edges, I encourage you to do it inductively, right? So especially in the case of these full M-array trees. So if you're going to have 4 children, then start with the root node and figure out how many internal vertices and how many edges are whenever you're at level 0, right? Whenever the height is 0, whenever you're just dealing with the root. And then apply the rule to get to level 1. And then you can see the jump. So you go from, however many vertices. You have 1 vertex initially, and then you add 4 children, and they're all leaf nodes. Right? But if you go to level 2, then all of the leaf nodes from level 1 suddenly become interior nodes, and then now you have 4 times 4 leaf nodes. Right? And so then it's all of the leaf nodes plus all of those interior nodes plus the root node. Right? And so you can come up with this formula on your own, and with just a little bit of jotting on the page and making notes to yourself and so forth. So you can derive this or a formula similar to this. The trick is whether or not we're following the convention that the root node is considered an interior vertex, or if we treat it as a one-off. But I won't test you on that. Right? It's just the convention of whoever you're working with at the time. Okay. So theorem, given a full M-array tree with n vertices, there are I internal vertices, right, where I is equal to n minus 1 divided by m. Right? So we have n total vertices, we remove our counting of the root, and then we say that the internal vertices are the ratio of all non-root vertices to the vertices per interior node, which makes sense. So vertices divided by vertices per interior node gives you, using stoichiometric operations, right, where we're applying rules of division and inversion and so forth to our labeled ratios. Right? Then the number of internal vertices gets flipped to the numerator, and I becomes the number of internal vertices. Right? So children per internal vertices. Right? Okay. And then L leaves, where L is computed by the vertices per interior node, right? Children per interior node minus 1 times the total number of vertices, and then that plus 1 divided by children per internal vertex. Okay. So we have these two computations, or we can be given internal vertices and total vertices and compute that we have n is equal to mi plus 1, right? And that's obtained from this formula. Multiply both sides by m, add 1 to both sides, and you get this. And L leaves, where L is equal to m times negative 1 times I plus 1. I'm not convinced this is correct, right? We already have this formula up here. I'll have to see what happened there. But this is almost certainly incorrect. The m should be inside here. And I equals n minus 1 divided by m. Maybe, but if it's just negative 1, then I would have pulled the sign out. So something happened here, and it got mislabeled. I give the page number that this is found on, so feel free to double check these formula for yourself, and you definitely should if you want to use them for computation. Okay, but this is almost certainly wrong, so double check that. And then given leaves and total number of vertices, then we can find this relationship between the total number of vertices, the m times L minus 1 divided by m minus 1, and then compute the number of internal vertices using this formula, L minus 1 over m minus 1. Okay. So there's, for full M-area trees, we can navigate between the total number of leaf nodes and number of internal nodes and so forth. But I feel like those formulae are all overkill. You should, we'll notice various patterns of full M-area trees, and you should be able to compute it without those. But whatever, they're there if you care to memorize them. Okay, so definition: the level of a vertex V in a rooted tree is the length of a unique path from the root to this vertex. So level 0 is the distance from the root to itself. Right? It didn't have to travel at all. To that first level of children, it's a length of 1. To the second level of children, the grandchildren of the root, it's a length of 2, and so on and so forth. So the level is the distance from the root, right? The number of hops you have to make to get back to the root. This is very similar to the definition of the height of a rooted tree, right? But the height is the maximum level. Right? So the largest distance between any node in the root is the height of the tree. Right? So that distance is going to be maximal for some leaf node, right? So you can say it's the maximum distance of any leaf node to the root. In other words, the height of a rooted tree is the length of the longest path from the root to any vertex. Okay. A rooted M-area tree of height h is balanced if all leaves are at levels h or h minus 1. And so this is indicative of like a sequential filling of a tree. Right? So if we have a binary tree or a ternary tree or whatever, it just says that we essentially go left to right and assign them until we have a full level. Right. So if it's a ternary tree, then each internal vertex can have 3 children. Right. So we fill that first level until there's 3 children there. And then we fill the second level until there's 3 squared children on that level, with each interior node having 3 children themselves. You fill the 3rd level until there's 3 cubed children there. You fill the 4th level until there's 3 to the 4 children there, and so on and so forth. But we're going from left to right, filling them in, sequentially. But if we stop before a level is completely full, we still say that it's balanced if all of the nodes are at those 2 levels, right? The previous full level, the one that we were able to completely fill up, and the one that we were currently working on, right? Kind of a one analogy for this, and you can debate whether or not it's apt, is like if you were to fill up egg cartons, right? So each egg carton has either 12 or 18 or whatever size egg cartons you're buying, right? Slots for eggs. And if you fill them up sequentially so that you don't start filling the next carton until the previous one is full, then you'll end up with, however many completed egg cartons, right? H minus 1 egg cartons. And then that Hth one, that last one, which has whatever the last overflow and the remainder of eggs were stuffed into that one. And so we say it's balanced then, as long as all of the others were full and they all live on, all of the leaf nodes live on one of those 2 levels. The last full level, and then whatever partial number of leaf nodes you had for that final level. Okay, so theorem, there are at most m to the h leaves in any emery tree of height h. Right. So remember that h is the maximum distance, and so the tree is essentially maximally full, or has a maximal number of nodes whenever it is full, whenever you stuff in as many as you can. This is reflected in the property that the leaves are also maximal if you stuff as many as you can. And so one way to think of this is to go in the other direction. So let's say you have a ternary tree where each internal node can carry up to 3 children. But you don't. You do something that looks like a linked list. You have a root, and it has a first child, and or a 0th child, and that one has a 0th child, and that one has a 0th child, and you go down h levels. You go down like 10 levels or something like that. Then you only have 10 nodes, right? Or 11 nodes if you include root, which you should. Then you have 11 nodes, right? And a height of 10, because a maximum distance of 10 from that lowest node to the root node. Right? Well, then you only have 1 leaf node, right? So that's whenever it's minimal, is whenever you create something that looks like a linked list. And so if you have an emery tree, it is maximally distinct from a linked list where you have that minimum number of leaf nodes, right? Whenever it's full, and you have the most number of leaves whenever each level is completely stuffed to the max, and then all of those leaf nodes are on that highest level or lowest level, however you want to do it. Okay, so corollary: if an emery tree of height h has L leaves, then the height of that tree is greater than or equal to the ceiling of the log base m of those number of leaf nodes. And this will apply later. We'll talk about that whenever we discuss decision trees, the height of decision trees. Okay, so applications. A binary search tree is a binary tree in which each child of a vertex is designated as a right or left child. No vertex has more than one right child or left child, and each vertex is labeled with a key which is itself the embodiment of the item. Right? If we had a binary search tree and we were storing strings or words or whatever, then the key would be the word itself. If we were storing numbers, then the number would be the word itself, right? So that's what we mean when we say the embodiment of the item. Furthermore, vertices are assigned keys so that the key of a vertex is both larger than the keys of all vertices in its left subtree and smaller than the keys of all vertices in its right subtree. So essentially, it says that the midpoint of any subtree should be the root, right? So that it falls between everything that happens on the left and everything that happens on the right. And so if a binary search tree is balanced, then you end up with something that has pretty quick search. And so there's a trick to maintaining a binary search tree, and we'll look at those later. So AVL trees are an example. And that's the one that we used last semester, I believe. And we may do an example of that again. But I guess we'll come back to that whenever we have access to the code. For now, let's just keep running through this. So a rooted tree in which each internal vertex corresponds to a decision with a subtree at these vertices for each possible outcome of the decision is called a decision tree. The abstracted execution path of a program or procedure may be represented using a decision tree. So if true, go left. If false, go right. So if else. So you can see how these decision trees make these branch points. And so we call them flow control structures and so forth, and they decide how we go from the set of possible inputs to the set of possible outputs. Right? So that is managed by flow control. And the structure, if we go back and we evaluate why did our algorithm do this thing at this point, we would use a decision tree to model it. Well, it came to it with this test, and the test evaluated to true or false or whatever, and it followed this path. And so we can count the number of operations. We can represent that using a decision tree. And so that is one way in which we can model the worst case runtime of an algorithm. Decision trees, we can think of them as being binary trees, right? Or we can think of them as being, as having any arbitrary number of children. If whenever the flow control construct that you're using is, rather than if and else, it's like if or else if, and then else or whatever, right? Some if, else if chain. Or a switch statement where you have one of many possible outputs. But I think at its base level, we can think of it as just a series of if and else statements, even if we're using loops, right? So the loops have these conditional tests, and if true, then continue in the loop. If false, then break out of the loop, right? So still this left and right behavior. Okay, so but that's the idea of a decision tree, is that it's this tree-based model of the actions of a program. Okay, so the theorem. The sorting algorithm based on binary comparisons requires at least log base 2 of n factorial comparisons. And so earlier in the semester we looked at a lower bound for log base 2 of n factorial. And we said that such a thing would be bounded below, right, is big omega of n log n. Right? So we can say that no algorithm which solves something using binary comparisons, right, on a set of n items can have fewer than this many comparisons, right, which is what our sorting algorithms do. Right? So corollary to that is the number of comparisons used by a sorting algorithm to sort n elements based on binary comparisons is big omega of n log n. So the best worst case runtime we can have for a sorting algorithm is n log n. You say, okay, well, why do you say it that way? Why don't you just say that the best runtime is n log n? Well, because that's not true. The best runtime is probably constant, right? So you write an algorithm and you hope that what you're given is input is a sorted collection, and you return that. So it doesn't solve it at all, right? Like it just spits back out whatever was put in. It doesn't attempt to solve it, and in that one case, 1 out of n factorial possibilities, it's correct. But that is the best case, right? It just spits it back out. But we wouldn't call it an algorithm because it doesn't return a correct response for most cases, right? So if you want something that actually solves the problem, you can do no better than this as your worst case runtime. But there are some algorithms like bubble sort, which both solves the problem and has a best case runtime on the order of n, where if the input was sorted, then it just iterates over the collection once and then returns it. But merge sort will always take this amount of time. It'll always be on the order of n log n, regardless of whether the input was sorted to begin with or was unsorted. But the upside is that it's never worse than this. And n squared versus n log n squared is significantly worse as the size of the input gets larger. Okay, so next theorem. The average number of comparisons used by a sorting algorithm to sort n elements based on binary comparisons is n log n. Right? So it turns out that a fair representation of the runtime for such an algorithm is to just measure the number of comparisons performed. Right? So in such a case, in the case of a sorting algorithm, the comparisons represent basically between half to a third of the work that's involved, right? So perform the test, and if you need to swap, then you make the swap operation. You create a temporary variable to hold location A's value. You assign value B to location A, and then you assign what was in location A to location B. Right? And so then you're performing 3 additional operations whenever you do that. If you're creating additional arrays and so forth, whenever you're breaking it up, then there's the work of creating that additional number of arrays. But it's in the case that a swap is necessary, or that some additional action is necessary, it's in direct proportion to the number of comparisons. It's 4 additional operations or X additional operations each time you have some comparison indicate that it needs a swap, right? So the average number will be, well, let's say that on average you swap half the time, right? That's a fair assumption. Then it's going to be 0 additional operations when no swap is necessary to X number of operations. So X over 2, whatever that constant ends up being, times n log n. Well, then the average was in proportion to n log n again. Right? So this one basically says that the average number of comparisons. So this one, this one just says that the average number of comparisons used by a sorting algorithm is in proportion to n log n. It grows on the order of that. Okay. Tree traversal. So we have a tree, we've stored it. It would only make sense to go through that work if we have some way of accessing the items stored within. Right? So procedures for systematically visiting every vertex of an ordered rooted tree are called traversal algorithms. Next definition. Let T be an ordered rooted tree with root R. If T consists only of R, then R is the pre-order traversal of T. Otherwise, suppose that subtree 1 and subtree 2 and so forth to subtree n are the subtrees of R from left to right in T. The pre-order traversal begins by visiting R. It continues by traversing T1 in pre-order, then T2 in pre-order, and so on until Tn is traversed in pre-order. See the example in universal addressing systems, 808. Oh, I guess I should have included that if I referenced it. Anyway, by intuition, this is a tree structure of a document outline. where the document itself is the root, and then the chapters are the first level interior nodes, then sections and subsections, and so forth. These addresses may be sorted by document, then chapter, section, and subsection, before moving on to the next section and chapter, and so forth. Right, so if you were to write it out, then you would write the title of the book, and then you would write the chapters, and then, if it was a table of contents, then you wouldn't list all of the chapters and then all of the subsections of those chapters and so forth. It would be chapter and then the sections within that, and then if there's any subsections within those sections, then that would come before the next one, right? And so you would see this this outline structure. So that's pre-order traversal, right? So the next one is in-order traversal, right? So let T be an ordered rooted tree with root R. If T consists only of R, then R is the in-order traversal of T. Otherwise, suppose that our subtrees go from left to right. The in-order traversal begins by traversing T1 in order, then visiting R. It continues by traversing T2 in order, then T3 in order, and finally Tn in order. Okay, so what am I saying here? So when we spoke briefly about the binary search tree, where the value that's at the root of any subtree is larger than everything to the left of it, all of its children and descendants that are on the left subtree, and smaller than all of the descendants that are in the right subtree, so that it's in between those two. So if you were to use an in-order traversal, then you would go, then your binary search tree would print out the sorted nodes of the tree from least to greatest, right? So you'd go all the way down to that leftmost child, and then you would visit its parent, and then you would visit the right child, and then you would go up and visit the level that's 2 away from the maximum height, or that leftmost height, right? And then you would print that out, and so forth. So we'll do pre-order, in-order, and post-order. We'll write a quick JavaScript program that does that for us. But we'll do that after the break. Again, when the focus switches more to coding. Okay, so let T be an ordered rooted tree with root R. If T consists only of R, then R is the post-order traversal of T. Otherwise, suppose that T1, T2, Tn, etc. Are the subtrees at R from left to right. The post-order traversal begins by traversing T1 in post-order, and then T2, and so forth, right? So the order, pre-order, in-order, and post-order that we refer to, always discusses what do you do with the root? Like, when am I supposed to print out whatever value the root is holding on to? Do I do it before I enter into the tree, the subtrees? Do I do it after, or do I do it sometime in between? Well, if you do it before, then it's pre-order. If you do it after visiting the left tree but before the right tree, then it's in order. And if you do it after visiting both the left and the right tree, then it's post-order. Right? Okay. And again, we'll get a chance to revisit that. Okay, so it's common for pre-order traversal, in-order traversal, and post-order traversal to be referred to as depth-first traversal. Though clearly that term is ambiguous, and these modifiers exist to clarify when to apply the action of visiting the tree nodes. So, for example, printing out the key name. And so again, this you'll become more familiar with it as we reinforce it. So I have some notes for myself to post some examples of the algorithms, right? But we'll go back through the notes and if not visit every algorithm, make sure that we take a look at a good deal of them. But I want you to see the codified version of each one of these algorithms rather than just pseudocode. I want you to see both and become familiar with how you translate from pseudocode into actual, executable code. But then also just how to go from thinking about a problem or some description of either a structure or a problem and turning that into code. So a lot of that is developing a process for yourself, and we'll work on that. Okay, so spanning trees. Right? So again, we start with a graph, right? And a spanning tree of some graph G is a subgraph that is a tree containing every vertex of G. Right? So we said that there is a certain condition that if it's satisfied for a graph, then it also happens to be a tree. A spanning tree is a systematic way of making that happen. Right? So taking this simple graph where everything is connected, and then removing enough edges such that you don't break the tree structure, but that you now have a tree derived from that graph. Right? And so it's possible that a given graph can have multiple spanning trees. There's no guarantee that whatever algorithm you have generates a unique spanning tree. But this just says that you've turned that simple graph into a tree without adding edges, but by removing enough edges to give it that tree property, right? The property that you have a unique path from any nodes A to B. Okay. So note that either a breadth first or depth first algorithm may be used to induce a spanning tree rooted at any node in the graph. Okay, theorem. A simple graph is connected if and only if it has a spanning tree. And that makes sense. So if your simple graph is not connected, then you won't be able to generate a spanning tree, or some tree from the graph, which includes every vertex, because it's not connected. It's missing an edge somewhere along the way that would make it into a single unit. Minimum spanning trees. A minimum spanning tree in a connected weighted graph, right? So the weights are the key here. Is a spanning tree that has the smallest possible sum of weights of its edges. So you add up all the weights, and if it's the spanning tree with minimum weight, then it is the minimum spanning tree. Okay, and now we have some algorithms, Prim's and then Kruskall's algorithms for how to generate those. And we're done, right? Back to background concepts. Okay, so when we return from the break, we'll focus a lot on coding. We'll go back and revisit all of these places where we have, this placeholder for algorithm, and we will implement it in either one or two languages. We'll spend most of our time coding. I would encourage you that as we go through it and do that, that you do it yourself, right? If you have your own computer, you have your own laptop or desktop or whatever, that you install, whatever software. It doesn't have to be exactly what I'm using, but something that will enable you to use the programming language that I'm using, so you can follow along. Or if I do the examples in multiple languages and you have something that supports one of the languages, then that'll be fine. I'll try to do JavaScript because you can use the console for from Firefox or Chrome or Edge or whatever in order to gain access to JavaScript runtime. So really, as long as you have a web browser, you should be able to code in JavaScript. But do work the examples along with me, and it'll be frustrating. You'll make really simple mistakes that it won't be obvious to you what you're doing differently than what I'm doing. But those are growing pains, and it's going to happen sooner or later. And I would encourage you to do it, to have it happen to you while you are paying for your education, rather than when someone is paying you and expecting quick turnaround on whatever it is they've assigned to you. Right? We'll get together and we'll put in the work, and we'll start that next time. And then after exam 2, then we'll try and mix and match or find the right balance between discussing proofs and things of that nature with programming and how to take advantage of our familiarity with writing code and using that to construct proofs or perhaps understand it a bit better, and vice versa, how we can use our understanding of proofs in order to write correct code, right? Code that is well defined, has its assumptions well stated. You can write test cases against it, and above all, it works. Right? Okay, so have a great spring break, and I will talk to you in a couple of weeks.